This part of the lecture is going to focus on the range of problems from 3 to 16 on MyOpenMath, so let's head over there. So here we see a vector. This vector, we don't even know where the x and y axes are when we're looking at this vector. It just seems to be existing somewhere in the xy plane, and we want to write it in component form. So if we don't even know where the x and y axes are, how can we write this vector in component form? Well, you may recall that two vectors are going to be the same vector as long as they have the same direction and the same magnitude. So it really doesn't matter where a vector begins or where a vector ends. What matters is the length of the vector, the magnitude of the vector, and the direction, which means that if I were to draw this same little vector from the xy plane, from the origin going out, if all of these vectors, I know this one's a little crooked, but if all of these vectors have the same magnitude and the same direction, then they are going to be identical. So what that means for our problem here is that we can actually just put the xy axis anywhere we want it to be. If we want to draw the x-axis and the y-axis so that the beginning of our vector is actually at the origin, then the resulting 3 over 3 down gives us 3, negative 3 as the label that we would use for this vector. So let's go ahead and look there at the answer then is 3, negative 3. So how does that work? Well, normally when you have a vector and the vector exists somewhere else, like let's say the vector started over at the point 3, negative 1, and then the vector went 3 down and 3 over, and so it went to 6, negative 4. The points that I am using here are written as points from geometry. They have the curvy sides of parentheses. And the curvy sides of the parentheses just tell me a point. They tell me where the vector begins and where the vector ends. But the component form gives us different information. The component form tells us ultimately the magnitude and the direction by this information. So this information is still telling me that I'm going 3 over and 3 down. And so by those 2 points, I can come up with this information, and this information then leads me to the exact same magnitude and the exact same direction. Okay, so next question. So in question number 4, you see again that J is starting way out here at negative 3, negative 1, and K is way over to the right here at 6, 2. However, we want to ask ourselves, what is really happening with this vector JK? How far over to the right does it go, and then how far up does it go? So you can see that by drawing yourself a little right triangle, that if you move from J all the way to the right to where K is located at 6, you see that we're moving to the right from negative 3 to positive 6, which is 9. And then we're going up from negative 1 to positive 2, which is 3, which means that the resulting vector is 9, 3. This information is expressing for us the magnitude and the direction. It doesn't matter where J is, and it doesn't matter where K is on the graph. What matters is the magnitude and the direction. Okay, so in this problem right here, we know that the magnitude is 6.25. And we also know that this vector lies along the negative y-axis. So if we drew a picture of this vector, this is what we would have. We have the negative y-axis. Whoops, that's the negative x-axis. Scratch that. Let's try that again. We want to go along the negative y-axis. That's important not to get those mixed up. So the length of this vector, the magnitude of the vector, is still 6.25. The question is, what point does the vector reach? What is that point down there? So we would label that point down there in our minds, because you can do this in your head, you don't have to draw it out. This point right here is 0, negative 6.25. So what does that mean for my components? Well, since I am starting my vector at the origin, in the case of starting your vector at the origin, the ending point is going to end up translating to be the standard position component form. As long as your beginning point is the origin, then whatever your ending point is going to be your answer. 0, negative 6.25. Okay, so here in this question, though, we are not on an axis. Instead, we have a vector in quadrant 2 that makes a 30-degree angle with the negative x-axis. So let's go ahead and draw this one. So here we have a 30-degree angle with the negative x-axis. Here's my vector that has a magnitude of 3. So what you see that we have is a right triangle, right? You can just drop down a perpendicular, and we're trying to figure out what the x and the y are. Well, then that's a basic SOHCAHTOA problem. If this triangle is that the sine of 30 is equal to y over 3, and the cosine of 30 is equal to x over 3. And of course, we can replace these values here then. The sine of 30 is 1/2, and the cosine of 30 is square root of 3 over 2, and then we solve for the variables. And y is equal to 3/2 and x is equal to 3 root 3 over 2. But that's based off a 30, 60, 90 triangle, and that doesn't necessarily correspond to this exact point right here. This point is in the second quadrant. So the x value then needs to be a negative value. And so we would write the component as a negative 3 root 3 over 2. And of course, the sine value is still positive because we're in the second quadrant. And this is the intuitive way of doing this. If you knew nothing about any formulas for vectors, you could still figure all this out using basic, well, what I learned in 8th grade, sort of trigonometry. The SOHCAHTOA concept and the Pythagorean theorem is enough to get you to answer all of these questions. But there are formulas that can help you get to the answers in a different way. So here's a fun little slide I found on the internet. A vector quantity has both magnitude and direction. Okay, so here's your vector quantity. And here they're representing the angle with the Greek letter phi. And so from this side right here, this side is denoted a sub x. And then this height here of the vector is denoted a sub y. And then they've shown you that the x value can then be represented by the magnitude of a times the cosine of phi, and the y value of the vector, the y component, can be found taking the magnitude of the vector times the sine of phi. So let's go back then to that previous problem and see how that applies. So the magnitude of this vector is given to us. What is the direction angle? The phi, the direction angle. Well, if you were to draw this vector, so here's your vector, and then from the positive x-axis to the vector is actually the direction angle of the vector. The direction angle of the vector is 150 degrees, which in that little NASA picture I showed you was represented by the Greek letter phi. So now we go to the formulas, and the formulas are that the y component is represented by this equation here. We have the magnitude of the vector times the sine of the direction angle, and the x component of the vector is the magnitude of the vector times the cosine of the direction angle. So in both of these cases, of course, the vector's magnitude gets replaced with 3. And then we have the sine of 150 and the cosine of 150 degrees. and then we just take, what is the sine of 150 degrees? It's 1/2, so then that's 3 times 1/2, which we end up with our 3/2. And then what is the cosine of 150? Negative root 3/2. So multiply that by 3 and we get negative 3 root 3/2. So we're back to the same answers that we had before, but we've found the answers in a different way. But the answers still are going to be that the vector components, which are written with the sideways v, is negative 3 root 3/2. Make sure you don't use parentheses whenever you're writing vector components. It's really important you do not use parentheses. And positive 3/2. So here then is the MyOpenMath answer for you. Look at question 7 next. A vector with magnitude of 7 points in a direction 310 degrees counterclockwise from the positive x-axis. So you don't have to draw the diagram. You can just use the very formulas we had just looked at. You're going to take 7 as the magnitude and multiply it by the cosine of 310 for the x component, and then multiply 7 times the sine of 310 for the y component. And since 310 degrees is not on the unit circle, then we're going to be able to use decimal approximations. So in this case, we want to have decimal approximations because we do not have a unit circle degree, whereas in this problem we did have a unit circle degree, so we expected to see an exact component. Okay, so now some fun things, vector graphing. So we're going to be graphing u and v, and then we get to graph the addition of u and v. So let's start with graphing u. So we start at the origin, and then we want to go negative 2, 2. So we're going to go back 2, up 2, and there's my vector u. And then for my vector v, I start at 0, again, 0, 0, and I go 0 over and 3 up. Now to get the sum of the two vectors, it's really nice. You just have to add the x-coordinates and add the y-coordinates. And if you go to page 338 of your book, you'll be able to see this, that vector addition and vector subtraction and vector scalar multiplication is super easy. You just add the x components and you add the y components. So the resultant is going to be at negative 2 plus 0, which is negative 2, and 2 plus 3, which is 5. So my resultant is at, let's start at 0, 0, of course, and then go to negative 2 and up to 5. And then once you graph all three, you can even visualize that you have a parallelogram. So vector addition in an xy plane is even easier than geometry vectors. Now when I look at the answer is drawn a little differently. Instead of drawing the second vector from the origin up 3, this particular approach, and notice it says one possible approach, is to draw your vector where you left off with your previous vector. The head-to-toe relationship I talked about in the previous lecture. So you can do it this way or you can do it this way. It doesn't matter. It's completely up to you. Either way, I will mark that correct. Okay, so here's vector addition again. All you have to do is add the x components and add the x components and add the y components. So if you add negative 8 and negative 3, you get negative 11. And then you add positive 15 and negative 4, you get positive 11. So vector addition is super easy. And what do we see here? These values are not the same. Okay, this is asking for the magnitude of this resultant vector. And so the magnitude is going to be, just take the Pythagorean theorem of this, right? Negative 11 squared plus 11 squared is going to end up being 121 plus 121, which is the same thing as 11 root 2. And here there's a decimal approximation, but as much as possible, anytime you can enter something in exactly, you should enter it in exactly. And sometimes the answer is written as a decimal, but still the MyOpenMath will still expect you to give an exact answer. However, in this particular problem, it does say round answers to the nearest hundredth if necessary. So there is that option. We do get to round in this problem, and we do get to write the answer as a 15.56. That would be rounding to the nearest hundredth. Now, these two are going to be taking, instead of negative 11 plus 11 squared, I should have shown my work here. Okay, so there you go. The vector magnitudes here are going to be, okay, we've got v, which has got these lengths right here. So you've got the square root of, so here are the components for v, and here are the components for w. And now we add them together, and we end up with the answer, which is 22. And that's because 8 squared plus 15 squared is 289, and that's 17. And then, of course, here we have a 3, 4, 5 triangle, and 17 plus 5 is 22. Okay, in question 10, first you just need to figure out what the components are for u and v and note those. And so for u, you have the component 3, negative 4. And then for v, you have the component negative 4, negative 4. So when you go to add all of these together, you just get to use, well, that's a negative as well. Both of those are negatives. So add u and v. Well, take your x components, which you get a sum of negative 1. And then take your y components. Negative 4 plus negative 4 is negative 8. Then u minus v. This is actually easy. You just take u and you subtract, sorry, this one's u. You take u and you subtract v. So the way that we would write it out is 3, negative 4 minus negative 4, negative 4. You'll like these problems. They're really nice on the brain. Okay, 3 minus negative 4 is 7. And then negative 4 minus negative 4 is 0. And then we get to go the opposite direction, v minus u. I'll let you do that. Just switch around these to the opposite direction. 2u, this is called scalar multiplication of a vector. So you take 2 and you multiply it times the vector u, which is 3, negative 4. And then the answer is just multiply the 2 times each of the components. It's going to feel like the distributive property. And there you go. So now let's see all of these answers here. Oops. Okay. I don't want that. Okay, here you go. Notice that u minus v and v minus u are opposites. This should not be surprising to us because we can switch this around by multiplying it by negative 1. In other words, u minus v has a scalar multiplication of negative 1 times v minus u. Okay, so this is a combination of scalar multiplication and addition. So we would write it out like this, and then if you want to have another step of intermediate work, you can do the scalar multiplication. It's not necessary to have this additional step, but if this helps you get to the correct answer more reliably, then of course it's completely encouraged. You do not have to show any work on these problems. And then you can just add these together, and negative 2 plus negative 6 is negative 8. 6 plus 9 is 15, and that's why our answer is, okay, what did I do wrong here? 6 plus negative 9 is what I meant to say, not 6 plus 9. 6 plus negative 9 is negative 3. There you go. That's how you do it. Okay, next problem. We're moving on now to question number 12. Here we're looking at the IJ form ij form is found on page 339. Now, this vector right here, normally to write it in component form, we would say, all right, you go back 3, and then you go up 5, so the component form is -3, 5. Now, this is actually the same thing as the sum of the following two vectors. So -3, 0 and 0, 5, these two vectors, if you add them together, we get here. So this is the resultant vector if we add these two quadrantal vectors, that is vectors that follow exactly along with the x-axis and the y-axis. Now we can further break this down into -3 times 1, 0, and then also 5 times 0, 1. And you may wonder why we would do that, and it's because of the definitions of the I vector and the j vector. So let me put those up for you. The I vector is 1, 0, and the j vector is 0, 1. Now if you look on page 339, you will notice that the book writes these a little differently. It writes it as a bold lowercase I and a bold lowercase j. You do not get to write a plain I and a plain j. You have to instead write with this little vector notation, because I that is not bold is the imaginary number I. So whenever you are handwriting vectors, you need to include the arrowhead, or half arrowhead at least. Only if you're a textbook that has a bold font can you get away with dropping the arrowhead. Okay, so if I is 1, 0, do you see this right here, 1, 0? This is I. And j is 0, 1, so then this one is j. And then let me go back to purple here, so I can now still say that we have 5 times j and -3 times I. So the answer here is -3i plus 5j. Now you don't have to do all this work. I was just trying to show you what is the relationship between these two forms of writing the same vector. This is one kind of component form, and this is another kind of component form. This is the ij form of vectors, and this is the usual component form that we typically see. And here is the answer expressed just like that. Okay, so I'm going to let you do question 13 on your own, figure that out, or watch one of these videos. Same thing with question 14. Now when we get to question 15, I will talk to you now about what is the dot product. The dot product has a definition on page 339, and it is that if you have these two vectors, u and v, and their forms are a, b, and c, d, then if you have u dot v, this is the dot product of u and v, then you simply multiply a and c, the x coordinates, and then you add to that product b times d. Notice then that the dot product is not a vector itself. The dot product is simply a number. So here we have vectors a and b, so we just multiply -4 gets multiplied times -1. And then we're going to add on to that the product of -6 and -8. You don't have to show this work, but I want to be really clear about how to do this. And we get 48 plus 4, which is 52. Okay, that's supposed to say 52. Hold on. That's better. 52. Ta-da! That's all you need to write down. So here we have the ij forms instead, but look, it's going to be the same thing. Negative 6 times 4 is negative 24. Negative 2 times 5 is negative 10. Negative 24 plus negative 10 is, moment of truth, negative 34. Shocking. Okay, so now what I'm going to do is make a third video to cover the last two problems.